This is problem 654E. It's on page 275. An insulated piston cylinder device initially contains 10 cubic feet of air at 20 psia and 60 degrees Fahrenheit. Air is now heated for 15 minutes by a 200 watt resistance heater placed inside the cylinder. The pressure of air is maintained constant during this process. Determine the entropy change of the air. Okay. So let's move in the slides from solids and liquids onto ideal gases. So the entropy change of ideal gases. And that's the only question, is to determine the entropy change of the air. So let's draw the system so we can understand what's happening. Here's state one. It's insulated. It's a piston cylinder. There's air inside of what I will define as my system. And there's an electric resistance heater with a power flow rate of 200 watts. 15 minutes elapses. And of course, what's going to happen? What do you think is going to happen if you turn on the heater and put energy into the air?
Air's going to heat up.
The air's going to heat up, it's going to expand, right? So you expect the piston to be moved up because you'd expect this to occur at constant pressure. Okay. Now the pressure in state 2 is the same as the pressure in state 1. They told us that this was a constant pressure process, but they gave us the volume in state 1 as 10 cubic feet, the pressure in state 1 as 20 psia, which would be the same as the pressure in state 2, and the temperature in state 1 as 60 degrees Fahrenheit, which by the way is 520 Rankine. Now we're supposed to find the change in entropy. Now the change in total entropy of the air will be equal to the mass of the air times the change in entropy per unit mass, right? Each pound mass of air is going to change its entropy by a certain amount. Multiply that by the number of masses and you'll get the total change in the entropy of all the air in the system. Now the change in specific entropy, this term right here, will just be the heat capacity of the air, and we're going to use an average heat capacity multiplied by the natural logarithm of the temperature ratio of the air, which is the change, R ln P2 over P1. Now go to the back of chapter 6, and notice we're not using these integral equations. We're using the integrated equations where we've assumed that the heat capacity is a constant. The only time you can do that is when the temperature change is not very high. We don't know what the temperature change is yet, but I'm going to start off assuming it's not very high and then determine if my assumption was reasonable or not. Okay? So, go to the back of chapter 6 in the summary equations and look for the equation there that I've written on the board. So go to page 269, about halfway down the page, under heading 3, you'll see the two equations. Now, why did I choose the second equation and not the first?
Because you were given pressure and temperature.
Because we're given pressure and temperature. Did you notice that the pressure remains constant, and so the natural logarithm of P2 over P1 would be equal to the natural logarithm of 1, which is 0? You can use either one of those two equations you want. It does not matter. You'll get the same result, but it's easier to use this one because then I don't have to deal with volumes. I can deal with pressures, which are known. Notice I don't know the volume yet in state 2. I expect it to be more. Okay. But notice that I need the temperature in state 2, but I don't have the temperature in state 2. How do you think we can find the temperature in state 2? Any ideas? We make a deposit of energy. Some of it's withdrawn via boundary work, yet some stays in here changing the temperature. What equation am I talking about? An energy balance, that's right. You don't get away from using an energy balance. I'm sorry. I know we're talking about entropy. You still have to use an energy balance. So let's do it. Let's pause on this for a minute because we need the temperature in state 2 before we can calculate this entropy change. So let's start off with an energy balance. Q minus W equals delta U. Is there any heat transfer in this system that I've chosen? There's a heating element. So is there any heat transfer?
It's all in the system. No, it comes in as work.
It comes in as work, that's right. So there's no heat transfer. Now you might look at this and say, well, how are we going to get it in? We'll put it in here rather than here. Because notice my system includes the heater. If my system just excluded the heater, then there'd be no work, there'd only be heat. Okay, I know it looks like we're splitting hairs, but I want you to understand this. Okay, so the heat transfer is exactly zero. There's only work that comes in. How much work comes in? Well, it's not 200 watts, right? That's power. We need to calculate the amount of work that comes in. How could I do that based on the power input? Remember, power input is basically a flow rate. It's flow rate of energy.
Over time.
So-
Yeah, it's time.
So multiply by time, right? So if you multiply the power input by time, basically you're multiplying flow for a certain amount of time. If I'm driving 50 miles an hour for an hour, I'm going to go 50 miles. If I put in 200 watts for 15 minutes, I'll get a certain amount of energy. Okay, so there's a dot. Yeah, we have 15 minutes of time here. So 200 watts, which is 200 joules per second, multiplied by 15 minutes of time. Of course, we'll have to convert. There's 60 seconds per 1 minute. And of course, we'd like English units here. So let's see. I did this in the context of the whole problem. We've got joules, so I'll need some calculator help here. 0.94782 BTUs per 1,000 joules. Joules will go away, we'll just have BTU. So grab your calculator, please. Multiply 200 by 15 by 60 by 0.94782 and divide by 1,000. What do you get?
170.6.
How much?
170.6.
Thank you. 170.6 BTUs. Anyone second that?
Yep.
Okay, thank you. So there's the amount of work transfer. Now, is this positive or negative work?
Negative.
Negative, because it's work flowing in. So this would be negative work in. Make sense? And that's equal to the change. Now, the change in internal energy of this system, how will the internal energy change? Well, wait a second. Have we got all the work that flows in or out? Remember, this is more of a summation, right? There can be multiple workflows. Are there any other workflows in this process?
Yeah, boundary work.
We've got boundary work that flows out too. We've got to take that into account. Now that's work flowing out. So is that positive or negative?
Positive.
Positive. So plus boundary work equals the change in internal energy. Okay. Let me write that just as change in internal energy and not expanding it. Now, what's special about the boundary work? Could you write down an equation for the boundary work? I know it's integral of PDV, but how would the integrated form look? I'll give you a hint. It's one of the forms I've already given you at the end of chapter 3.
It's pressure times delta V, right?
P delta V, isn't it? This is a constant pressure process. So this would just be P delta V. Now what we can do is, let's not forget this. Let me just get rid of this bit because we don't need it anymore and say the work input is 170.6 BTUs. Okay, that way we don't need this. We can actually work with the energy balance. Notice what we could do. We could say work in, which is this piece, which represents the electrical work in, equals the change in internal energy less the boundary work. Now we have to be careful because the boundary work equation is positive for work flowing out. So everything's okay, it's still consistent, but you have to watch that and be careful about it. Let's see. Well, wait a second, I made a mistake. I should have a negative sign here. What did I do wrong?
Negative.
Oh, I forgot my negative from here, didn't I? Boundary work flowing out is positive, so I should have plugged it in positive here, and I would get a negative sign from the equation. I hate the sign convention in this class. We get rid of it once we get to 320 and talk about work flowing in and out and heat flowing in and out. But we have to deal with what we've got now. So I made a mistake. There should be a negative sign from the equation. So then we'd have plus boundary work, but boundary work is just P delta V. Well, what could we do with this? Well, this is U2 less U1, which is the internal energy change, plus P V2 less V1. Okay, now this is a common trick you'll see. Anytime there's a constant pressure process, okay, you'll see the boundary work be combined with the internal energy change. Let me show you what happens. U2 plus, now if I distribute this, it would be P2 V2. I could write it as P2 V2, right? It doesn't matter if it's P1, P2, or just P. It's all the same pressure. But then we'd have minus U1 from here, minus from this product, P1, V1. Okay, now my U's look like V's, my apology, there's a U. So this would be U2 plus P2, V2 minus U1 plus P1, V1. Do you recognize U plus PV? What do we call that? Internal energy plus flow energy is what? It's not entropy.
It's an enthalpy.
Enthalpy.
Yes.
So this is H2 less H1. Okay? All we've done is use a little trick to combine the boundary work that the system does with the internal energy change. Basically what we've done is we've somehow related the withdrawal to the account balance change. Okay? Those two are not just independent things because this is a constant pressure process. So what that really means is we can write this, let me get rid of this again. We can write this as H2 less H1. Okay? Now why would we do all of that? Well, because we could write this as MCP delta T. Notice what I've done here is I've said CP delta T is just delta little h, in other words, the specific enthalpy change. If I multiply that by the total mass, then I've just got the enthalpy change. Make sense? And that's where we're going to get our temperature from, because this would be mCp of the air, T2 less T1. The only unknown in this equation now is T2. So solving for the temperature in state 2, we should get, I'm working this differently than I did in my notes, but that's fine. mCp, as we divide that out and add T1. Now you've already told me the work in is 170.6 BTUs. The mass of the air, do we have the mass of the air? No. Can we get the mass of the air? Sure. We've got V, P, and T, right? Putting those together, I'm not going to show you the details because you guys know PV equals MRT. So you can solve for M. It would simply be PV over RT. Let me just write down the result. The amount of mass in the system there it is. 1.0384 pound mass. Okay? No point in going through the ideal gas law and the details. You'll have to look up the gas constant for air. You plug in PV and T, and there you have it. Okay, so straightforward, simple stuff. Now, whoops, we're already working here. So the mass is 1.0384 pound mass. We need the heat capacity of air. Now we need the heat capacity at constant pressure. You probably don't have the heat capacity at constant pressure memorized, but you can find it. Go back to the beginning of Appendix 2. You need to see where all this stuff comes from anyway. Give me a page number once you're there, if you would, please. It's the very first page of Appendix 2.
884.
884, thank you. So we need the heat capacity of air, CP. Look on the right-hand page, it's probably the easiest place to find it. Air or water is the first one. I think air is the first one. 0.24, good.
BTU per pound of mass per Rankine.
That's right. So 0.24 BTUs per pound mass per Rankine is the heat capacity of the air at constant pressure. What we've done so far is we've taken care of this bit. We've got the work in, the mass, that's a 0, and the heat capacity. We have to add to that T1. T1 is just 60 degrees Fahrenheit. Have I made a mistake? I have not made a mistake yet because this is just the change in temperature. Now if I want to use these temperatures later in this ratio, then I will have to change the Rankine. Right now it doesn't matter. Okay? Now in my notes I went ahead and I added this to the 520 Rankine because I knew I would need Rankine anyway. Okay? So anyway, this comes out to about 1204.6 Rankine. If I calculate it in Fahrenheit, I just had to add 460 to it, and I get the same thing. Okay? Because basically this term is just a change in the temperature due to the energy that flows into the system. Make sense? The more mass there is, the less that energy is going to be able to change the temperature. The higher the heat capacity, the less that energy will be able to change the temperature of the air. Okay? Of course, the more energy that flows in, the more it's going to change the temperature of the air. So there's the temperature in state 2. So now, finally, let's calculate the specific entropy change. And I'll need calculator help here as well because I did not write down this intermediate result. But the heat capacity CP is still 0.24 BTUs per pound mass Rankine. The temperature ratio will be 1204.6 Rankine over T1. T1 is 520 Rankine. Notice our units will not change at all. So please grab your calculators and take the natural logarithm of 1204.6 over 520 and multiply that result by 0.24.
0.2016.
Thank you. Anybody second that? Okay, good. Don't need the energy balance anymore. All we really needed was the temperature in state 2. We've used the energy balance to find it. And in fact, we used it to find the specific entropy change. So now the total entropy change will simply be the mass, which is 1.0384 pound mass, multiplied by the specific entropy change, the entropy change per unit mass. Okay, pound mass go away, but BTUs per Rankine. When you multiply this out, you should get 0.209 BTUs per Rankine. And there's the total entropy change of the system. So the entropy of the air increased during this process. That shouldn't be too much of a surprise. The temperature of the air went up and the volume, the space that the air has to occupy, went up. Both of those would cause an increase or would be interpreted as an increase in entropy, an increase in randomness. Okay? Work flowed out of the system, work flowed into the system. Notice that the work that flowed in is a very irreversible thing because it was all transferred to thermal energy. So you would expect that entropy would be generated, which also lends to the idea that the entropy should have gone up. Since work flowed out, there's no way that this boundary work could have carried entropy with it. Okay, so everything says the entropy should have increased, and it did. Okay, questions? All right.